Now turn to Section 4. Section 4. You will hear a lecturer discussing the possibility of creating nuclear fusion. First, you have some time to look at questions 31 to 35. Now listen carefully and answer questions 31 to 35.
We look at the sun, a huge ball streaming out essentially limitless energy into space, and we think about how we need that energy here on Earth. Our oil reserves are running out, coal burning causes much pollution, and nuclear energy has many dangers. But where does the sun itself get its energy? The answer is that the sun makes it using fusion, or, more specifically, in a hydrogen fusion process. There is no pollution, no radioactivity, no waste products, and we have plenty of hydrogen. So, hydrogen fusion seems the perfect answer to our energy needs, and scientists have long attempted to achieve it here on Earth. So what happens during this process? The first step is to make two light atomic particles approach. In the case of our sun, these are hydrogen particles, the lightest and also the easiest to deal with. However, the problem is that the nuclei of atoms have electric fields, and fusion between these particles is opposed by their similar electric charge. They most naturally repel each other, and the nuclei of all elements are exactly the same in this respect. Thus, in order to overcome this repulsion and force them together, in the second step, the particles are heated. The trouble is, you need a lot of heat, incredible temperatures of the sort only seen on the surface of the sun. This is many millions of degrees, far higher than the melting point of any known material. Still, the concept is simple. The hot, wildly moving particles, which are now called plasma, will crash into each other, resulting in the third step, the fusion into helium, which releases energy and begins a self-sustained process.
Before you hear the rest of the lecture, you have some time to look at questions 36 to 40. Now listen and answer questions 36 to 40.
So, we know how fusion works. Thus, the big question is, can we create it here on Earth? We actually have the technology to superheat hydrogen into plasma, but no container on Earth can deal with those temperatures. Thus, we need to confine this superheated material so that it doesn't touch anything. For that, we need a special reactor, and most research has focused on an apparatus known as a tokamak system. That's Tokamak, an acronym from some Russian words meaning toroidal chamber with magnetic field. It's an apt name, since a very powerful magnetic field is used to confine and suspend the super-hot plasma in the air so that it doesn't touch anything. This is possible only because this plasma has an electric charge, which interacts with the magnetic field. Of course, the walls of the fusion vessel will still get hot, very hot, and to avoid being melted, they must be cooled with a cryogenic system to intensely low temperatures. But now we are faced with the second problem. If we are to draw power from this system, the reaction must be continuous and controllable. However, when fusion begins, the plasma becomes unstable, and at these temperatures, that is a very serious situation. If we lose control, a disaster could result. Despite the obstacles, in 2010, a European device managed some success, but needed far more power to generate the fusion reaction than that produced from the fusion itself. Obviously, then, it was not useful as a power source. More to the point, this system could only sustain a fusion reaction for a fraction of a second. Yet, to self-sustain, the fusion needs to run for at least 10 seconds. And the future looks bleak. Unfortunately, most scientists predict that many decades will have to pass before fusion power can become a practical reality.
That is the end of section 4. You now have half a minute to check your answers. That is the end of the listening test. In the IELTS test, you would now have 10 minutes to transfer your answers to the answer sheet.